Okay, so in this video, we're gonna uh, take a look at this section 9.2, which is moment generating functions or MGF of the sum of independent random variable. Okay, so let's see if we have random variable x, we have random variable y, and both of them are independent from one another. Okay, so let's say w is the sum of x plus y. Okay. Now, if we want to find out what is the PDF of this random variable w, which is the sum of these two, it's not very straightforward. It's quite complex, right? So first, you have to find the CDF, right, of this random variable w from the joint PDF between x and y, right? So if you know the joint PDF between these two random variable x and y, then you can integrate under the graph, right, with the region that's corresponding to x plus y. Once you get the CDF, then you differentiate the CDF to get the PDF. Okay, so there are many steps to get to the PDF, and then from the PDF you can find the moment. However, if uh, you can also find the moment generating function of W. This is a lot easier if you know moment generating functions of x and y. Okay, so we use phi to denote moment generating functions of random variable w with argument s. Okay, so what is the definitions of this MGF? It's the expectations of e to the power of s, this is argument, multiplied with random variable w. So basically you average this, right, over the PDF of w. Okay, now since w is x plus y, okay, so we plug that in. Or you can split this into two terms, right? E to the power of sx multiplied with e to the power of sy. Since random variable x and y are independent from one another, that means these two terms also independent from one another. That means the expectations of the product equal to the product of each expectations, right? You can separate the two terms like this, right? This only happen when x and y or these two random variables are independent. If they are not independent, then we cannot just split the expectation in this way. Okay. Now, if you look at this first term, this is the expectations of e to the sx. So this is the MGF or moment generating functions of random variable x. And the other term is corresponding to moment generating functions of random variable y. So at the end, if x and y are independent from one another, the moment generating functions of the sum of x and y is basically it's equal to the product of the two. Okay, so let's see the example. So we have example 9.3.2. This is from the problem at the end of the chapter. So we have random variable y, and we happen to know the moment generating functions, which is phi y. It's 1 over 1 minus s. Okay, so you see that this is function of s. S is the argument of the moment generating functions. The other random variable v has MGF, right? Phi v equal to 1 over 1 minus s to the power 4. And we know that y and v, right, these two random variables are independent from one another. Okay, we define the sum, which is random variable w. Okay, at the end, we want to find this second moment of w, or expectations of w square. Now, if we know moment generating functions of w, then this is straightforward. But before we get to b, we do a first. So first, we find the mean, the second moment, and the third moment of random variable y, which we know the moment generating functions. Okay. So first, the mean or the first moment, we can find this by differentiate the moment generating functions of y. We differentiate with respect to s, and then we substitute s equal to 0. So that means we're going to differentiate this. I hope you still remember how to differentiate. So differentiate this, negative 1 comes down, 1 minus s to the power of negative 2. And then you differentiate in the factor with respect to s, you get extra negative 1. Or at the end, this is the derivative. Okay? And then you plug in s equal to 0. The answer is 1. Okay, so the mean of y is equal to 1. For the second moment, we'll find the second order derivative and then plug in s equal to 0. Since we already get the first derivative, right, which is 1 over 1 minus s squared, right, this term, then we differentiate one more time, right, to obtain the second derivative. Okay, so the second derivative is 2 over 1 minus s to the power of 3, and then we plug in s equal to 0. The answer is 2. Okay, so the second moment is equal to 2 for random variable y. The third moment, we use the same principle, but now it's gonna be the third order derivative with respect to s. Okay, so we differentiate one more time, right? This is the second derivative, second order derivative. Differentiate one more time, we get the third order derivative, which is 6 divided by 1 minus s to the power of 4. And we plug in s equal to 0. The answer is equal to 6. So the third moment of y is equal to 6. Now we move on to part B. Okay, we want to find the second moment of w. That means if we know the moment generating functions of w, then we uh, differentiate twice and then plug in s equal to 0. Now remember, w is the sum of x plus y, right? Or rather x I'm sorry, x and it's not x, it's v and y, right? But we know that v and y are independent of one another. Okay, so the moment generating functions of w would be the moment generating functions of v, right? So this is v, not x, multiply with mgf of y. Okay, so this is given from the problem. We multiply, we get 1 over 1 minus s to the power of 5. Now, if we differentiate one time, right, then we get 5, 1 minus s to the power negative 6. We differentiate one more time to get the second order derivative, right? You get 30, 1 minus s to the power negative 7. And now we plug in 0. Once you plug in 0, you get 30, and that's going to be the second order derivative. Okay, so if we have MGF available, then finding the moment is just a matter of finding the derivative and plug in 0. Okay, so let's go back. Okay, what if the random variable w is the sum of more than two random variable? For example, x1, x2 plus xn. So we have n random variable. If all of these x1, x2 to xn are independent of one another, if that's the case, then we can conclude that the MGF of W is equal to the product of the moment generating functions of each random variable. Okay, so finding the product is a lot easier than try to find the PDF or CDF of W from the joint PDF of x1 to xn. Okay, and if right, in addition to independent, if all this x1 to xn has the same PDF, so it's the same type of random variable, uh, we call this identically distributed. That means that they have the same distributions or same CDF or same PDF. So for example, x1 to xn, right, has the same distributions as random variable x with PDF fx and the moment generating functions phi x. So that means the moment generating functions of w would be the product of each one, and each moment generating functions are the same because it's the same type of random variable. Then basically it's moment generating functions of x raised to power of n.